So today our speaker is master student Stuart Edris. Stuart graduated from OU in 2018 with 2 bachelor's degrees, one in geography and one in meteorology. Stuart then became a graduate student on the meteorology side to keep doing math and coding. He has been working as a research assistant to Dr. Jeff Basara for about a year or so and plans to finish his master's degree this summer. Today he'll be speaking to us about climatological analysis of flash drought criteria. And with that, I'll hand it over to you, Stuart.
All right, thank you. And thank you everyone for coming. This will be a overview on my master's thesis and sort of where it's currently standing. Before we get to that, just want to give a few quick acknowledgments, largely to my advisor, Dr. Basara, as well as to Jordan Christian, Ryan Wakefield, who all 3 of whom have been providing pretty constant feedback, thoughts, direction, and throughout this project as it's been developed, as it's been evolving, and so on. And I want to thank my community members as well, with Dr. Ilston and Dr. Selesky among them, as well as mention several organizations to help sponsor this project and help keep it going. The USDA National Institute of Food and Agriculture, NOAA's Climate Program, NASA Water Resources Program, USDA Southern Climates Plains, or Southern Plains Climate, sorry. With that, we can start. And just to start, I can give a quick overview of just a quick review of what flash drought is. And flash drought is basically droughts that develop over a relatively short time period, where normal droughts tend to develop over the course of months or longer. Flash droughts tend to develop over the course of a few weeks to maybe a month or 2. And this can have several large ecological impacts. One example is seen here, with 2012 being one of the more famous flash droughts in recent history, where over the course of a little over a month, most of the landscape has been desiccated, most of the vegetation has been killed off just by the rapidly drying conditions. And one of the largest impacts flash droughts can have are on agriculture. Again, citing the 2012 flash drought, which has some of the largest crop losses that I know of to date, particularly in Iowa, with some places being beaten only by the 1993 floods. However, flash droughts have only been recognized and relatively recently. It was first mentioned in the introduction to the Drought Monitor. However, it took over a decade after that for anyone to really start studying it. And the first time it was flash droughts were really looked at was by Atkins et al. In 2013, who used the Evaporative Stress Index, or ESI, over the course of several weeks, derived from thermal satellite data, to sort of look at flash droughts over and investigate them based on various famous case studies, such as 2000, 2003, 2011, and so on. In more recent years, flash droughts become more prominent. More studies have been coming out investigating it. Many other methods have been looked at to identify and quantify flash droughts, such as the soil moisture index developed by Hunter et al., or the rapid change index, also developed by Atkins et al., and various other studies besides. However, there has not been, and even to the present, there still technically isn't any real consistent definition or way to identify and quantify flash drought events. And this is one of the things that's largely addressed in a recent paper by Atkins et al. In 2018, basically trying to get the community to come together and agree on a consistent definition for whatever end is to use it, stating some criteria focusing on the rapid developments, and that there actually had to be drought going on. That is, the index was below the 20th percentile. And one of the studies that tried to adjust it, that came from here at OU, was done by Christian et al., who developed methods to identify and quantify any flash droughts that should work for any gridded data sets. It's a method that uses primarily SESR and uses 4 criteria to identify flash droughts. And sort of using these criteria, we can break apart flash drought into various components, into the flash components or the rapid intensification, as well as the drought components, and examine them individually. And that's sort of the goal of this study, is to take that method, break apart flash droughts, sort of examine the climatology of each of the main components, and determine how, see if we can determine how prominent each component is to the development of flash droughts. For example, is rapid intensification play a more important role in developing flash droughts, or and what are some of the events surrounding the presence of rapid intensification, but say no droughts? And the way we do this, and the method that uses this using SESR. So we start with, to get SESR, we start with the evapotranspiration, or ET, and the potential evaporation, or PT, which is collected from the North American regional reanalysis model, which has 32 by 32 grid point resolution over a 3-hour temporal resolution from complete data set from 1979 to 2019. So 40-year data sets, and effectively take the ratio of these 2 variables, ET to PET. And this ratio describes sort of the evaporative stress over a grid point, hence the name, the evaporative stress ratio. And additionally, for since this ratio can have a lot of variation, and we're more concerned with the overall trend in the ESR as compared to this diurnal variation, the ESR was averaged into the pentad timescales over 5-day intervals. In addition to this, the ESR was standardized using this 40-year climatological data sets, creating the SESR, or SESR. And since we're also interested in evolution of drought conditions over time, we also calculate the change in SESR from one pentad to the next, and that change is also standardized. And the standardized change and SESR itself are what is used for the flash droughts analysis. So the actual criteria used for this analysis are a foreign number, and we'll be going back and forth with this. And the example we have here from the Christian et al. Paper developed this. The first criteria is that the flash drought has to be at least 30 days in length, or 6 pentads. In addition, the SESR has to be below the 20th percentile, so that's our drought condition. In addition to this, our third criteria is that the change in SESR, or the individual change in SESR from pentad to pentad, must be below the 40th percentile. That is, drying must be occurring over the grid points. However, one exception is allowed for some moderation. For example, if some precipitation falls over the area and it helps moderate, but not enough to prevent the flash drought from actually occurring. So, and finally, the fourth criteria is that the overall mean change in SESR across the entire flash droughts, which is this dashed line here, is must be below the 25th percentile. And so the algorithm that I sort of developed to this calculates each of the criteria individually. So that's one benefit, that we can sort of take this flow charts and sort of break it down into each criteria and see what each of them mean physically, individually. And we're going to do this in the most sensible way possible. That is, we're going to skip number 1 and go straight to 2. And criteria 2 is our drought criteria. It's the one that checks that there is actually drought occurring over that grid point, and is the one that follows from the Atkin et al. Paper. And that one's pretty straightforward and pretty easy to understand. Next is we're going to keep skipping criteria 1 going to 3, and this is checking for any drying that's occurring. So having the standardized change in SESR be below the 40th percentile means that it is checking that there is drying going over that grid point. Furthermore, since this is over the pentat timescale, we can sort of use this to identify when the flash drought begins and ends. So if we go back to our example, the flash drought is defined to start whenever criteria 3 is true, or when it first becomes true, and ends whenever criteria 3 becomes false. So with that in mind, we can now finally go back and look at criteria 1. Criteria 1 requiring that each day, or sorry, requiring that the total total drying period is at least 30 days in length, is largely meant to sort of filter out dry spells, short-term low drying events that have little impact that we're not really concerned with. However, we can also sort of interpret this as the criteria 1 is checking for continuous drying events. Since it must be at least 30 days in length, we're looking for drying periods that last at least 30 days. Additionally, and finally, we come to criteria 4, which states that the mean change in SESR between the start and end of the flash droughts must be below the 25th percentile. The algorithm checks that criteria 1 is true and requires it to be true for criteria, for this one, for criteria 4 to be true. This is largely because as the algorithm loops from one pentat to the next, it can have a start date at, say, grid point number 5, and then at grid point 6, it could perform that mean that would be below the 25th percentile. But since that's only a mean of, say, about 5 days, it's not necessarily representative of what we want. So requiring that criteria 1 be true ensures that the mean that the algorithm calculates are over the 30-day intervals, and that it checks that the overall change in SESR is rapid enough that this drying event, this drying period, can be considered a rapid intensification, can be considered the flash component of our flash drought. As such, for this study, identified the flash component or the rapid intensification of flash droughts to be criteria 4, since that's effectively what it looks for. In addition, the drought component is simply criteria 2, since that is our criteria that is concerned and looks for actual droughts. As an additional thing that should be noted is that this algorithm identifies rapid intensification and identifies flash drought retrospectively. So it will only identify flash drought and rapid intensification at the end of the drying periods, and not during or beforehand. So keeping that in mind, a lot of the maps produced by this algorithm will be shown at a sort of monthly timescale, and it'll be showing sort of the percentage of days that's in which the criteria are true. So in this case, the percentage of days in which meets drought condition. And since this is a new method, or one that's I've developed, it should be verified against things we know. And I chose to verify it against 2012 since that's a fairly well documented and well-known case at this point. And sort of comparing the drought components with the drought monitor, we can see that the algorithm seems to have performed fairly well. It captured the overall area of droughts in the in the Great Plains and Midwest fairly effectively, as well as this little pocket of droughts in the southeastern U.S., as well as a couple areas, say, up northeast. And it continues to identify drought somewhat effectively in August as well. There is some caveat to this in Texas, but overall continues to identify droughts in the Great Plains, the slow pocket in the southeast, and so on. So it seems to be identifying the drought fairly well. But what about for the flash components? And moving on to here, it should also be noted that the flash components comes out much less frequently than the actual drought component. As a result of this, the scale on the color bars between the flash component and drought components will always be different. The droughts will range from 0 to 100. That is either from no days in that month experienced drought to every single day experienced this month, to the flash component, which goes from 0 to only 20%. It's much less frequent, largely due to the fact that involves examining conditions to evolve over a 30-day period. So, and things that's, things evolve over 30-day periods. So looking at the flash components and how they perform, comparing to the analysis of 2012 performed in the Basara paper, the algorithm captures the flash components fairly well in May in northern central Kansas. However, not so well in central Missouri. Possible reason for this is being that the intensification ended almost at the end of May, so the algorithm would have only identified rapid intensification on, say, the last 2 or 3 days of the month. In addition, this intensification is not quite as strong as some of the other time series we'll see. So this one could be one of the more iffy timescales of being actual rapid intensification or not, and the algorithm identified it as not. Looking at June, the algorithm seems to perform fairly well, and then finding rapid intensification that's going on in northern and eastern Oklahoma, and particularly in central Nebraska, where there's a lot of rapid intensification being recorded in the time series. And of course, since it's 2012, we can't really escape any discussion of Iowa, particularly western Iowa, where there was very stark, very rapid decrease in SESR in the months, or from June into July. And the algorithm does seem to identify that as intensification, that rapid intensification. So overall, it seems to perform fairly successfully in identifying where the flash components of flash drought. One caveat being in Missouri, potentially due to the timing of the event ending straight at the end of the month, or that it may not be quite as strong, or necessarily as strong as needed to be identified. So with this method, we can sort of take the same approach we have that previous studies have, such as in the Otkin et al. Paper in 2013, to sort of examine flash drought on a case-by-case basis. So doing that, we can sort of take this algorithm and see what it says about relatively well-known droughts. For example, 1988. And this one seems to identify fairly persistent droughts occurring throughout almost the entire month, starting in May, to having wide outbreak of drought, very widespread event throughout the vast majority of the US in June, that is persistent throughout the entire month and remains in the parts of the Midwest into the Appalachian area throughout the rest of the summer season as well. As for the flash component, it's identified a fair amounts of rapid intensification going on from May into June in the sort of the Corn Belt area from Iowa, northern Illinois into southern Minnesota and Wisconsin, which makes some sense as that's the area the drought sort of expanded westward from May into June. The algorithm also identified some rapid intensification going on in the Intermountain West, which something that will become a bit of a running theme throughout. And if you just sort of look at the flash drought identified, which is basically when droughts and the rapid intensification are both true simultaneously, we find that it matches up with the rapid intensification or the component very effectively once you get east of the Rocky Mountains. So this might be some indication that perhaps the flash component plays a slightly more important role, or more prominent role at least, in the development of flash droughts, but that's only one case, so we can continue looking at others. For example, we can continue looking at 2003, which started out with some drought occurring in eastern Oklahoma into northern Missouri and northern Iowa, southern Wisconsin, and Michigan. They remained pretty persistent into the Wisconsin, Michigan, and northern Iowa area into June, and then started to really develop in the Great Plains during July, and then rapidly develop and propagate westwards in August. Given that there's little drought in the Central Plains in June, one might expect there is some intensification going on there, and especially over the Corn Belt area where it quickly goes from little to no droughts in July to persistent drought throughout the entire month of August. And the algorithm does indeed pick up on that. It picks up the rapid intensification that goes on in southern Nebraska, northern Kansas, and sort of watches as it propagates into central and eastern Iowa, northern Illinois, southern Minnesota in August. Again, with some points being identified in Intermountain West. And if we again look at the actual flash drought identified, this again matches up pretty closely with the rapid intensification. So this helps support the earlier hypothesis that that plays potentially a more prominent role. If we look at another famous event, 2011, the algorithm seems to correctly find very large persistent droughts occurring in the southern plains in the southern United States, as well as the coastal plains throughout most of the summer months. Since this is a fairly well-known event, we can also compare this to the drought monitor and see how it performed, and see that it captures everything fairly successfully. It captures the drought in the southern plains, going out into the coastal plains. It even captures some of the gradients and drought between eastern Oklahoma and Arkansas. So SESR by itself seems to be representing drought somewhat effectively, better than we had originally anticipated it would. As for intensification, the algorithm spotted some, again, in the Intermountain West with our running theme there, but largely, again, sort of picking out the Corn Belt area, Corn Belt and soybean area for a lot of that to occur. And that's where the flash droughts for 2011 largely occurred as well. So the algorithm seems to be performing fairly well with these well-known events, but so a question then arises, how well does it perform with a more moderate drought events? One that would be more debated per se. For example, 2019. So last year was a fairly interesting year. We started the summer, May into June, with above normal precipitation, with it looking like it would be a pretty strong pluvial year. And then going into July, the precipitation stopped, decided it was done with the US and moved away to other parts of the world. So without the precipitation, there was a lot of drying that occurred over parts of the US, including some of the coastal plain areas. In this case, the desert Southwest being identified makes some sense, as they had a bit of an off monsoon year, with the monsoon coming much later than normal. So in this case, when we look at rapid intensification, it makes some sense that there's some in the desert Southwest, given the lateness of the monsoon then. However, it didn't really pick up anything much in the central US, much at all. So it appears that while there was a lot of drying and potential drought throughout 2019 or the later parts of 2019, it was not rapid enough to be considered flash droughts. There was no flash component to it. So as a result, there was no flash drought to it. So it performed, it seemed to give some results as to an intermediate case. Next, we can look at the overall event. So an interesting that one might look at is identifying where, identifying areas in which frequently see rapid intensification on a climatological average. And that's what this is showing here, is the percentage of the years in our 40-year climatology data sets that see some kind of rapid intensification. And we can see hotspots that are picked out over the corn and soybean belts, as well as some of the Great Plains, sort of weaker hotspot over the lower Mississippi area, as well as the coastal plains, and a much stronger signal in the Intermountain West, as well as Central Valley, largely over the Colorado River Basin. This could potentially be due to a combination of the monsoons in that area as well as the aridity. So whenever the monsoons fall, there is the landscape's very arid and doesn't really retain moisture very well. So there's a lot of rapid runoff that the NARR is just seen as lots of evapotranspiration going on. So it's identifying that as rapid drying going on in that area. Or it's possible that the NARR is just not handling the complex terrain very well. If you compare this to the climatology from the Criterion et al. Paper, it actually lines up fairly well. We get the same hotspots over the corn and soybean area into the central and southern plains, as well as the lower Mississippi Basin and the coastal plains. So this really does help support the idea that at least east of the Rocky Mountains, the flash components, this rapid intensification, plays a fairly important role in the development of flash droughts. However, we'll notice here that Intermountain West is not highlighted at all. So this does show that it is important to have an actual drought, where Western US is fairly dry. So reaching below the 20th percentile in SESR would potentially be more difficult than somewhere further east, where you see more variation in the climate. In addition, it's worth noting that I went ahead and omitted the climatology for the drought component, since that is criteria 2, being the 20th percentile for SESR. So almost by definition, the drought component would be 20% everywhere, which is what we found. So I've omitted that since it's a fairly simple map. So in wrapping things up, the algorithm seems to have separated the flash and drought components fairly effectively. Some possible exceptions in the Intermountain West that needs a little more investigation to see if the NARR is handling that well, or if it's some physical mechanism that's going on there. SESR alone was able to represent droughts better than we anticipated, which is a very positive result. Um, in addition, it seems like east of the Rocky Mountains, the flash component plays the more prominent role in the development of flash droughts. However, the climatology that we looked at was a very broad one, and the case studies that we looked at were very widespread drought events, widespread enough that one could argue that um, you only needed some rapid intensification just to set off any kind of flash drought events. So so for future work, a slightly more comprehensive look at the prominence of the flash components needs to be looked at, says looking more at the finer scale, sort of doing a more quantitative analysis to help look at that, as well as further work needs to be done in sort of identifying sort of the physical mechanisms that go into driving these components, where the physical mechanisms that goes on to this rapid drying in the landscape that we observe in flash droughts, where the mechanisms that allow these rapid drying events to occur, but necessarily no drought to be around, or where the mechanisms that allow droughts to be around, but or droughts to be present, but no rapid drying events. So that's some of the work that needs to be done. And here are the references used for this presentation, if anyone likes to see them. And with that, I'll take any questions.
Thank you, Stuart. So everybody should be able to unmute themselves if they so desire, and we are now open for questions. So any questions for the speaker? Okay, I have one, Stuart. So if I understood the methodology that you described correctly, the way that you were breaking down the contributions into the drought and the rapid intensification portion, that rapid intensification portion required a 30-day window, correct?
Yes.
So is it possible that that 30-day window would be impacted by fairly weak and short-term positive trends in the SESR data?
If there was more than one, yes. At that point, criteria 3 would be flagged as false, and that would not be identified as a rapid intensification. If there's some variation on the smaller scale, say on the diurnal side or the daily scale, that one potentially not as much, since the pentad should average that out and be looking at more of the overall trends. And for that, we're just looking at, is it decreasing consistency with the allowance of one moderation event?
Thanks. Any other questions for our speaker?
Hi, Stuart. This is Qingyu. Really like your slides. So to physically understanding the criteria of for the four criteria, the criteria one is saying that it is actually a drought. The criteria the criteria two is said that it is physically a drought. Criteria one together with criteria three is saying that from a time range and from the physical measurement range, it is a rapid increase, so it is a flash. I'm trying to understand the physical representation of the criteria 4. What is the mean delta SESR is representing here?
So essentially, criteria 1 is saying we have some rapid drying that's occurring. Is it over a long enough time span to sort of weed out dry spells and be considered sort of a flash drought event? Criteria 4 what it does is it checks that overall drying period was rapid enough to be a flash droughts. So you can have some drying that can occur, but may not be rapid enough for it to be flash droughts. One of the better examples for this would have been 2019, which had some drying, but was not enough for it to be considered the flash component of any drought.
Yeah, cool. Another question from me is that, so basically all your analysis for the case, the figures are plotted in a monthly average, or?
Yes. Basically, it is on a month-by-month basis, averaging all of them and seeing, yeah, it's actually just an average of them. Since everything has a true or false value, the average gives us a sort of percentage of how many days within that month was the criteria true.
Right, that is great. So I was looking at the other case studies 2003, and I compare the results from June to May and to July to June. Looks like if we do a minus between the two adjunct, from between the two months, it looks like the first component, which is a flash component, is really correlated to the difference between the 2 months. And that also makes sense when you are saying that it appears that the flash component of rapid intensification is more prominent driver in development. But I know the reason why. I mean, it looks like true, but I don't physically understand why the first component is the driver in the development. It has been proved with the previous slides, and that is really well showed from the color between different months, right? But why that is a kind of a signal as a development of that.
Hey, Stuart, do you mind if I interject just briefly?
Go ahead.
That is the exact topic of Ryan Wakefield's dissertation.
Okay, sorry.
So no, just come back later. That is literally, she's on here. She could probably interject at some point, but when we actually get into the physical mechanisms of the development and spread, that's literally her dissertation. So
okay, so it's an advertisement.
Yeah, there you go.
Thank you for the ad.
And in the meantime, Stuart, you can thank me for saving you a little bit of grief that way.
Yeah. Thank you.
Thank you, both.
Okay, any more questions for Stuart before we wrap up today? Last call.
Yeah, could you go back to, it was one of your last slides with the climatology of the flash drought over the US?
For the rapid intensification or the flash drought as a whole?
Either one. So I'm just noticing a pretty stark grid point to grid point difference in the interior highlands area of the US, so washtop mountains and the Ozark Plateau. Do you think that is a physical difference, or do you think it has to do with something like terrain similar to the Mountain West?
That could certainly be due to the terrain, since the Pacific West is a very moist area that partly due to the mountains receives consistent precipitation at certain parts of the year, as compared to Eastern Washington, Eastern Oregon, where it dries off very rapidly. You start to enter more of that precipitation gradient zone, which previous studies have shown that's where a lot of these interactions that help stir up these rapid drying events are strongest. So it's definitely possibly a physical terrain feature.
Okay, any more questions? All righty. So I think that's probably all we have. So I'd like to thank Stuart and also all the other students that have made it through this virtual seminar series. I know it's been a hard adjustment, but I think everybody's done a really nice job, and I appreciate everybody's willful cooperation and showing up every week.